Assalamualaikum and hi everyone. Okay, so in this video I'm going to talk about collision theory. It's very important for you to understand about collision theory because this is related about the formation of product. Alright, so only successful collision can produce a product. Without a successful collision, no products will produce. Okay, every reactant molecules will continue to collide, but some of the collision might be successful, or sometimes we refer it as effective collision, but some of it might be unsuccessful collision. Okay, so only successful or effective collision can lead to the productions of product. Okay, so there are two different conditions that need to be fulfilled in order for a collision to be successful, which is first one, okay, so the reactant molecules must have kinetic energy greater or equal to the activation energy. So what is activation energy? I'm going to elaborate further about activation energy later on towards the end of this video. And secondly, the reactant molecules must collide in the correct orientation. Okay, so other words of successful collision, okay, we refer it as effective collision. Okay, some reference book might be referring successful collision as effective collision. Okay, so don't get intimidated by this one. Okay, so how does a correct orientation means? Okay, so for example, I'm trying to form HCl from the reaction between hydrogen gas with chlorine gas, okay, to produce 2 HCl gases. Okay, so I need to collide between these hydrogen molecules with chlorine molecules. So collision must take place between these two different molecules in order 2 molecules of hydrogen chloride must be produced. Okay, so in this first one, okay, so I arrange my hydrogen and chlorine molecules in this side by side. Okay, so when they collide, okay, so this hydrogen will collide with this chlorine, and this hydrogen will collide with another chlorine atom in the chlorine molecule. Okay, so they are facing towards each other. Okay, so H collide with the chlorine and another H is colliding with another chlorine atom. So these two can form bond, okay, resulting in the formation of product. So in this first one, products form because orientation is in the right place. Okay, so correct orientation for this one. Okay, what about the second one? Okay, so in the second picture, instead of side by side, and now I'm arranging my hydrogen molecules on the top and my chlorine molecules in the bottom. Okay, and then I allow them to move forward, thus resulting in this H atom to meet this chlorine atom from the chlorine molecule, and this another one hydrogen atom to meet the second chlorine atoms in the same molecule. So they can collide with each other, they are facing with each other, so they are having a correct orientation and directly can form bond between them, and therefore HCl can form. So in this second setup, okay, it's still a correct orientation, so product can form, so it can have a effective collision to take place. Okay, what about in the third one? Okay, so in the third one here, so in this one, okay, this is my hydrogen molecules and this is my chlorine molecules. Okay, when I allow these two molecules to collide with each other, only one of this hydrogen atom is colliding with the chlorine atom. Okay, so one of the hydrogen atom is colliding with one of the chlorine atoms from the chlorine molecule. So only one H and one Cl is colliding perfectly and can form one HCl, whereas the other hydrogen atom that is present and the other chlorine atom that is present does not facing each other, so they are not in the correct orientation. So as a result, okay, in this setup is not a correct orientation. Okay, therefore, okay, not a successful collision takes place, or unsuccessful collision is taking place. So in this one, clearly no product can form. Okay, so only in these two types of orientation there are possibility for product to form. Okay, because it's already fulfilled one of the requirement for a successful collision, which the molecules must collide in a perfect orientation or correct orientation. Okay, so for a product to form, they must fulfill another one requirement, which is to have kinetic energy greater or equal to the activation energy. Okay, so what is the activation energy? Okay, so activation energy is sometimes referring to as EA. Okay, so you're going to see more on activation energy when you learn thermochemistry in your chapter 2 semester 2. Okay, so activation energy is referring to the minimum energy required to initiate a chemical reaction. Okay, if you're learning biology, it must be familiar to you about the activation energy, but since you are in the module 2, you don't learn biology, so this might be a first time for you to hear activation energy. Okay, so for any reaction to take place, any reactant molecules must have kinetic energy at least equal to the activation energy. Every chemical reaction has a specific value of activation energy, so it is a fixed value and there's nothing that we can change about it. Okay, but in order for a reaction to achieve a kinetic energy equals or to overcome this activation energy, heating process is needed. Okay, so heating process is needed for the molecules to gain kinetic energy to overcome the activation energy, because through heating process, the kinetic energy of the molecule will be increasing. Higher temperature, higher kinetic energy. Okay, so why do we need to overcome this activation energy? Because when we are able to overcome the activation energy, means we have the ability to break the bond between the reactants, and we can form a new bond to form between the product. Okay, so there are two different types of reaction that you need to understand, which is exothermic reaction and endothermic reaction. Okay, so exothermic reaction, exo here means, okay, release heat to the surrounding. Okay, whereas this endothermic means absorbing heat from the surrounding. Okay, so we can determine either a reaction is exothermic or endothermic based on the given value of heat reaction, which is your delta H. So your delta H can be positive or it can be negative. So positive indicates for endothermic and negative means it's for the exothermic reaction. Okay, so this is an example of a chemical reaction which they give you the enthalpy of the reaction is negative 392 kilojoules. Okay, so that means the forward reaction, okay, so the forward it means from left to right, is an exothermic reaction. So for every value of enthalpy reaction given is for forward reaction. Okay, so you're going to understand more again about this enthalpy of reaction in your thermochemistry. Okay, energy profile diagram for exothermic reaction, and the second one is for endothermic reaction. Okay, so I always refer it as exothermic reaction to be moving downwards. Okay, going down the hill. Okay, because as you can see, the curve is going down. Okay, whereas in endothermic reaction, I refer it as going uphill. Okay, so uphill. Okay, so in exothermic, it's going down the hill. Okay, that's how I remember this type of sketch. Okay, so in energy profile diagram, so we have here the y-axis to be the potential energy. Okay, and the x-axis to be the reaction progress. Okay, so in any energy profile diagram, you must label where is the activation energy. So this is the activation energy, okay, EA for my exothermic reaction, and this is the activation energy for my endothermic reaction. Okay, so in the same energy profile diagram, you also need to label the value of enthalpy of reaction. Okay, so since we have two different types of reaction, which is exothermic reaction and endothermic reaction, okay, so you need to be alert about the directions of the arrow for exothermic and endothermic reaction. Okay, as you can see, in the exothermic reaction, the arrow for the enthalpy of reaction is moving downwards, whereas for my endothermic reaction, enthalpy of reaction is going upwards. Okay, so for a complete energy profile diagram, you must always include this axis, label the axis, potential energy and reaction progress. Okay, and then where is the activation energy? So activation energy is consisting of this double-headed arrow. Okay, and for your enthalpy of reaction, either moving downwards or moving upwards, and it's just one-sided arrow. Okay, and label the value as well if you are given the information. Okay, so there are two types of energy profile diagram. One is going down the hill for exothermic, and going up the hills is for endothermic. Okay, back to the questions that we discussed before. Okay, which is the reaction between ozone and oxygen atom to produce oxygen gas, and they give you the value for activation energy for the forward reaction and the enthalpy of the reaction, and you need to determine what is the activation energy for the reverse reaction. Okay, so we have to draw our energy profile diagram for this one. Okay, so these are the given information. Okay, so since the enthalpy of reaction for this reaction is negative, it means it is exothermic reaction, so it's going down the hill. Okay, you start by plotting this energy profile diagram for my exothermic reaction. Okay, so this is Z, and then we have to label. Okay, so our reactants here is ozone plus oxygen gas. Okay, we are forming 2O2 gas. Okay, then we have to label where is our activation energy. So activation energy is here. Again, is double-headed arrow. Okay, ups and downs. So our EA equals to 19 kilojoules. Okay, and then our enthalpy of reaction, since it is negative, so it's from here, it's going down. Okay, so delta H equals to negative 392 kilojoules. Okay, this is the activation energy for your forward reaction. Okay, so that means if it's going in the reverse direction, it becomes an endothermic reaction, and and your activation energy is now from here, from the top until the end here. So this is the EA reverse. Okay, so if you have to calculate, so EA reverse is actually the sum of EA forward, okay, plus delta H of the reaction. Okay, so ignore the sign. Okay, negative or positive, we just need to sum up the value. So 392 kilojoule plus 19 kilojoule. So you're going to get 4. Okay, so 421 kilojoule. 421 kilojoule is the value for the activation energy for the reverse reaction. Okay, so let's now move forward to the transition state theory and activated complex, which you can see in the energy profile diagram. Okay, so what is activated complex? So activated complex is a temporary species which form by the reactant molecules during the condition before it breaks to form product. So at this state, there are a bond about to break between the reactants, okay, and the same time a bond is about to form between the products. Okay, since this activated complex is just a temporary species, it only exists at the transition state. Okay, so transition state is the highest peak. Okay, the highest peak in your energy profile diagram. So highest peak in the curve of energy profile diagram. Okay, that means since it's highest peak, it has the highest energy value. So highest energy value, highest energy, or KE, and so, or potential energy. Okay, so since it have the largest kinetic energy value or potential energy or energy, it's really unstable. So your activated complex only exists at certain period of time, or your activated complex only exists for a couple of seconds before breaks down to form product. Okay, so let's look and label where is your transition state, okay, based on your energy profile diagram. I have here my energy profile diagram for both exothermic reaction and endothermic reaction. Okay, I told you just now, okay, so activated complex is just a temporary species which exists at the transition state. Okay, so where is the transition state? Transition state is the highest peak in your curve in the energy profile diagram. So these are the transition state. Okay, so label here transition state. Okay, at the highest peak. So again, I just want to remind you, so what is activated complex? A temporary species with large Ke and it's very unstable. Alright, okay, so in the transition state theory, they only just want to explain to you about the activated complex which exists at the transition state. Okay, you're going to learn more about transition state later on when you learn about mechanism in the organic chemistry. Okay guys, so basically we are done for this video. We already talked about collision theory. Okay, we talked about the requirement for an effective or successful collisions to take place. Okay, in the same time, we already discussed about activation energy, and from the activation energy, I taught you two different patterns of energy profile diagram. One is for exothermic and another one is for endothermic, and I already give you an examples on how to calculate the activation energy for the reverse reaction based on the given value and given chemical equation for the forward reaction. And in the same times, I already introduced to you about activated complex and transition state theory. Okay, see you guys in my next video. Bye bye. Thank you for watching.